But because the time is limited, so I usually will list the proof of the results. And now we start. We will work on real numbers or complex numbers. So I assume that you all know what is a real number and what is a complex number. So we start with the basic definition of vector space. So a vector space or F is just a set but with some extra structure. Namely, we define a set V with an addition. So we can sum up any two elements in V. And also there's a scalar multiplication defined. That means we can let a number in F multiply with an element in the set V. This addition and scalar multiplication must satisfy some properties. The first one is commutativity. That means if V1 and V2 are just a member in V, that will imply that the sum of V1 plus V2 is equal to V2 plus V1. And this will hold for any V1 and V2. And for any element in the set V and the associativity. So this means for any three elements, we can first sum up the first two of them and plus the third one, or we can first sum up the second one and the third one, and then we plus the first one into the sum. So this means the multiplication, although the addition is associative. There is this additive identity. So this means there is a vector in V which is special for the property that for any small v in the set V, V plus 0 is 0 plus V, because V itself. Later we will know that this is the zero vector in the vector space we will call. And there are should also exist the additive inverse. So this means for any v, a vector, we have a vector w also in V. I mean, a member W is also in V, such that V plus W equals to this zero vector, to this special zero element. And we usually denote W by minus V, the negative of V. W is called the inverse of V. So our list should go on because we need other properties to define the vector space. So we have the one in F such that it multiply any vector V in V, it multiply any member small v in the set V is just V itself, and it is also okay if we multiply from the right. In fact, we should use the dot notation for the scalar multiplication because I know it here. However, usually we will just omit the dot when there's no ambiguity. Now we did one property to relate the addition and scalar multiplication. We require that for any scalar lambda we have, any u and v equal to v, we should have the equation. The sum of u plus v multiplied by lambda should equal to the sum of lambda multiplied u and lambda multiplied v. And for any number 1, number 2 we have the sum of lambda 1 and lambda 2 multiplied by v is equal to the sum of lambda 1 times v plus lambda 2 times v. Yeah, by the way, you usually write an arrow to indicate that this zero element is a vector, is a number in V. So this is the definition of a vector space over a field F, where F is R or C, and we call the elements in V vectors. In some places, you will see that they are also called points. But we will not use this term here. Okay. Yeah, is it the more or just I erase them? Okay, I will erase them. So we have some examples. So if our vector space V has only one element, namely it has only the zero vector. This is a vector space, but it is so trivial. We will call it zero vector space. But yeah, it is not funny. We are going to look at some funny things. So we can let V is just F. all the properties I just erased that apply immediately on the set F. So this is a vector space, and F itself is a vector space over F. And the further one is we take F is R, and V is C. We know that this means C is the collection of all the numbers Z equal to x plus iy, where x and y are real numbers.
Yeah.
So, as a vector space, we can just write elements or vectors in C as a pair consisting of two components of coordinates x and y. And the usual addition of complex numbers is defined component-wise. And if we identify a complex number with a pair of its real parts and imaginary parts, we note that the sum of two vectors on the plane is defined component-wise also. And the rest of the other properties can be checked easily. So this means C is a vector space over R. And to interpret in C as a vector space over R, we need two parameters or two freedoms. Is there any question?
The y is not r squared.
Yeah,
Two numbers.
we can also denote this that C is a two-dimensional vector space over R, and this notion will be used later when we use information about the basis of the vector space and also the dimension for vector space.
Okay.
I erased the figure.
Yeah, probably we should first write on that whiteboard.
So, okay.
Yeah, but we can do it later.
Yeah. You pause it.
Huh? Sure.